Well, you know how to share your screen, yeah? It's and we'll just get started. So this is Peter Davis from Thales, and he's going to tell us about simulators and where they fit and why they don't fit sometimes. Yeah. Okay. Thanks, Peter.
Right. So I'm hoping that I've managed to get the front screen up.
Yeah, you have. It looks lovely.
Okay, and I will talk about that. I'll talk about this in the context of the automotive sector. I say the automotive sector rather than cars and things in relation to this, as a way of limiting those sorts of things, or talking about those sorts of things as we go along. Just so you know who I am, that's me. I don't really go and major on a lot of these things. I guess the bit at the bottom there might be the one that's of interest. So I have a playbook of almost 20,000 or 2,000 catastrophic attacks, many of which attack the machine learning and the AI. When you talk about catastrophic, those are the sorts of things that stop nations, stop food supplies, those sorts of things. So I've been doing that over quite a long period of time, and none of these get published for obvious reasons, but the principles that sit behind them are some of the things that I'll talk about as we go through this. So I guess my angle on this is not the angle necessarily of is simulation useful in demonstrating things do what they want to do, what I want them to do, when I would like them to, or yeah, under some occasions. It's the angle of actually looking at what happens, yeah, through life, what happens if it's attacked, what happens if the system changes around it. So that's the angle that I'll bring to these sorts of things. I've structured this as what are we trying to achieve, the outcome, what are we trying to achieve it on, and the domain. Because I think I've been very conscious in listening to other talks in this sequence that aspect of what is the domain and how do you want to do that turns out to be quite important. The simulation of digital twins, I'll talk about some of the evidence that we get. I'll try and attribute it as far as I can. If I miss an attribution, it's not because I don't like them. It's simply that I've forgotten. So please ask, and I'll try and make sure I put that back in, and what the answer might look like from my point of view. Some of the questions is, so how's machine learning AI different from your regular complex system? So what is it that I have to do specially or not to do specially because of that? And where are you using it? The most important thing, or one of the most important things for me, is the understanding of the failure modes of these systems. What is the standard and type of evidence required of your machine learning system, and particularly what is required of that when you're looking at what can the simulator do for you? So I thought I'd put this up as a starting thing. This is a putative press article from 2031. It was used for, and it was done on our behalf by RISCs, as so the Research Institute on Socio-Technical Research, based on feedback or information that we gave them, looking at how would boards of directors need to look at things going forward. You'll see in here things to do with automatic lane keeping assist, which is obviously one of the big things that we're looking at the moment. The AI capabilities of that, how will evidence actually be looked at in relation to that? The idea that we actually haven't got the data necessary to be able to make the justifications and things that going there. And this was designed to try and get people to understand in a board of directors what it was that they were going to be responsible for talking about and how it might matter. It was also designed to try and explain to some of my cybersecurity colleagues why data privacy wasn't necessarily the big thing. If you go killing people, that might actually turn out to be more important to people. And the systematic aspect that goes with some of these things. We worked with Burgess Salmon, who many of you will know they're specifically really very good at looking at accidents and accidentology in the legal framework. And they've worked with us carefully and closely on looking at how does cybersecurity go into the law and what we're trying to do. So in terms of what are you going to have to say to people, this was part of what we were doing there. So the sorts of things that we looked at were these sorts of things: personal injury, fatal risk, physical damage, disruption. And why am I going through this? I'm going through this because this affects what your simulator has to provide evidence for. So looking at these sorts of things as we go through there, it was clear we had elements to do with criminal law, the things that we needed to be able to give answers in relation to. It was clear that we had answers that we needed to provide in relation to civil law, and they were not the same sorts of things, and it was not the same evidence that we found that you needed in relation to those sorts of things. Some of those are much more probabilistic, some of them much more adversarial, particularly in the case of the criminal law. It generally takes place when there's been an accident, somebody's been hurt, injured in some way, and it's therefore entirely retrospective in what it's looking at. So the fact that you designed something well, ipso facto you did not design it well because the accident took place. So those are the sorts of things that you get into that. There's speculation, and in some industries areas you get the fact-finding processes that go with these sorts of things. Close to me, that's the Shoreham air disaster that we got there, that goes with these. And those are elements that you get there. The sorts of reprise here that we have from there, from the presentation they did for us, of reasonably practical and everything that you should have done. And the most important thing being, as we have recently determined in the CAM-CAV area, that's the mobility and automated vehicles area, we have a situation where it is perfectly possible to prosecute under normal health and safety regulations there, which weren't intended for this, but this gross disproportionality of things and the need to be able to do those sorts of things is there and embedded in what you actually need to do. And generally, regulation in this country is being used in order to lighten the burden of those sorts of things. So if there's an adequate regulation, you may determine that you don't want to go in and provide all of the health and safety stuff there. The other one that people like VW asked us to bring in on this one was the observation that the people that actually go after them are the financial conduct authorities for mis-selling the values of their bonds and things when they claim that they're able to do things that they're not actually able to do. And into all of these, this is what our simulator has to produce: contributory evidence or evidence in order to be able to determine that we're actually doing the right things. So these questions, these sets of things that we have here, are actually the outcomes of things that we need to do. So what we determined on the basis of this, if we started going through these things, was, if you look at the left there, that what we needed to have was a methodology that went with these things that was capable of being tested in court or by publicly appointed regulators. So if we have a methodology that says that it's absolutely determined and dependent on the simulation, then that simulation has to be able to be tested, and what it is able to do has to be able to be tested in court. We must be in a situation where operators understand what evidence should be produced by it and are able to measure the quality of that evidence. And very often we found, particularly where you have complex and large complex systems and cybersecurity considerations in relation to this, the ability to actually put probabilities or to put qualitative judgments with any certainty against these sorts of things is actually extremely questionable, and is one of the major failings that we found when we looked at simulators in relation to these things. And finally, that the evidence produced is capable of being tested in the courts. So what you get out of what you're doing, most particularly, this must become something that we can engineer, not something that we can guess at and wave our hands. And we must be able to operate it at the scale and the pace that the systems that we're in are changing. So we then looked at this. This is part of a system that we run in order to do real-time monitoring, to do the bit over the right-hand side. And we looked at where were we finding AI and machine learning in our systems. So these are pods, a couple of pods that we run at the moment. We're part of a project that's looking at how we'll be able to run those autonomously on the road without a safety driver. So you have autonomy operating in the overall system that's driving those. You have autonomy operating and machine learning operating in the sensors that goes with those things. You have machine learning and AI operating in the monitoring and adjustment elements that go with those sorts of things. You have it operating in the things that's actually selecting candidate cases for simulation, is actually using AI as part of that one. We've got digital twins and AI model training that are taking place, and the entire intelligence database that's coming here is being informed by artificial intelligence to one sort of thing as it comes from various places. And I guess the point that I wanted to make in relation to that, when we talk about simulation, or when we talk about what we're going to do in relation to this complex interaction of different evidential requirements and different sets of things you might need to do, operates inside a complex supply chain and a complex supply ecosystem, but it is overlaid by this requirement to have things. So as an example here, in order to be able to, when they're looking at the pods here, one of the reasons this system has been constructed in the way that it has is the observation that environmental changes rather than software changes or changes to the AI system were in fact causing the system to be operating in a way that was not expected. They were happening at a rate of 1 every 10 microseconds, which was a rate at which human beings were not capable of keeping up with that. So the need to have some sort of automation in terms of the selection of what you did, the feedback of how you might feed things back into that, and clearly what you were potentially updating was safety critical material going into those devices. So all of a sudden people were starting to ask about, well, what is the because it's only people or companies that can be legally responsible, what is the simulator, what is the software, and how does that go together, and what does evidence look like that would allow me to take that on? And the answer almost universally was a resounding silence in relation to that. And that was, if you like, one of the most basic areas of doing these sorts of things. So how does a set of software that is automating these things using AI and machine learning relate to the safety critical software that then is being downloaded into sensors and things of that nature that go into there? The 3 boxes across the bottom are extracts of actually what you need for what does evidence look like if you actually have to take it to court. So we put those up there. So particularly things like digital forensics is meant to be based on science, not supposition. So when you go to court, you are not supposed to say, well, I think it was okay. You're supposed to be able to give these kinds of things. I'll pause for a moment. So what were we trying to turn out? So we were trying to turn out a system, and it is important that we're turning out a system that has obligations not just at a moment in time, but through life. And it was extremely important that in putting that sort of thing, you needed to be in a position where effectively you had justifiable and enduring confidence that it'll function as expected, when expected. In the case of a car, consumer law would mean that that would be a minimum of 8 years, maybe 15, maybe 30, but at least a minimum of 8 years that you're looking at that. And we laced into there at the bottom the fact that if it's cyber secure, it needs to be able to display this property in the face of an adversary. Interesting as that is, that's kind of not the main thing, because the emergent properties of these systems are now really significant in their operation. They are also really significant in the economic viability of the products of the organisations that are based on them. And we put in the middle of there a poisoning attack against a machine learning algorithm on a brake sensor, which I have to thank my colleagues from the Imperial College for. This is an attack that is essentially systematically destroying the brake sensors. or a brake sensor on a vehicle. The point about it, it was attacking the machine learning that is being used in order to get maximum sensitivity out of sensors, which is one of the really big growth areas in the industry at the moment, being able to get as much as possible out of a sensor. And this attack successfully attacked not one vehicle, which would be the equivalent of I can saw through the brake pipes, but successfully managed to create an attack that applied to over 70% of the vehicles that had got that sensor on. So essentially, it triggered a logic attack against the complex and AI-based system that was operating above it, which was shocking, really, in relation to that. So part of the observation there is the implication of a lot of these things is now so great that the requirement for evidence is now governed by that. And when we look at simulation, how does it fit in relation to that sort of thing? So normally I bring up a car at this point. Actually, that's not true. I don't bring up a car at this point. I bring up this slide in order to talk about what a car is and how it all fits, and why I chose cars as a way of looking at AI, machine learning, why I use this as a way of actually looking at what was going to be required in relation to that. So honestly, the reason I chose automotive and transport as the sector in relation to that is because it is an industry. It is clearly bottom up, whilst most of my colleagues seem to believe that they're doing these things from the top down. It is multinational, it has regulations, it's price sensitive, but it is the very definition of a complex system. And into this, we're trying to put the types of techniques that you guys are interested in, and we're trying to apply the kind of governance that you guys might be interested in relation to this. So it doesn't really matter where I do these things. The most important thing is most of it is outside of my control, and most of it I don't have the data to do a wide-scale simulation of this system. We also came out with principles and observations that also apply to machine learning and AI. So looking at these sorts of things and looking at what your requirements are. So if you took these, the ability to analyze, the ability that behaviors must be bound, this observation that paradox of digital systems, that it can be both unpredictable and deterministic. The most important thing that we were trying to observe out of this is that as soon as you have elements in which the physical world is associated with your digital world, the combinatorial explosions of these things are huge, and we get to a situation where effectively I have an infinite attack space, and it is almost by definition something that can't be controlled. So I do get people saying, well, that's not true, but the counter thing that we ask people to look at in relation to that is, so when you have an accident, when you go to court, is it going to be acceptable to say that I have this wonderful reason why my digital system was working correctly, or are they going to start from the fact that you actually had an accident? And it's the physical behavior of these things that is actually the thing you have to be justifying, and that gap between the physical and the digital aspects of these things is the first area that makes it extremely difficult to model and to simulate the sorts of things that you're looking at. That is an infinite space, and you're not able to do that sort of thing. So when you talk about the adequacy of the modeling, that is a really difficult thing. It's a really difficult question to answer. We also observed that in almost all of the systems that we looked at, we were looking at systems under which there was conflicting objectives. So the way that people tend to do things in order to get an outcome at any level of certainty is to do a small scale system that is only designed to do one thing. The science would suggest that's the way that we need to do that. At the bottom of a single individual machine learning decision making system, that is what you would see. But the issue is that it joins into a complex system, and it's the complex system that we're actually interested in. And most particularly, the objectives of these are not necessarily consistent. It is not necessarily the case that what you would want to do from a safety point of view is the same as what you would want to do from a privacy point of view, and is the same as what you would want to do from a business point of view. It is not necessarily the case that the evidence that you're looking to collect in relation to that is the same. And very often, when you connect into a system such as the ones on the right of this page, where they're all joined together, you have a situation where small differences in the way that people choose to prioritize safety, privacy and business value on one component of the system compared to another one, essentially these are the changes that are actually meaning that systems can be broken on a systematic basis if we need to do so. And indeed, not just that they can be broken, but as part of their emergent properties, that they are almost certain to be systematically breakable. So what does that mean on the digitalization? So we clearly went from a situation where we did physical testing, and with machine learning and AI, you guys are recommending that we should do simulation on top of that. But my observation is that by the time we put the cyber resilience on the top of that one, that is in fact the bulk of the area that you're looking at. So the fact that I would not choose to drive from London to Edinburgh without having first simulated that the system was capable of doing that, so I would not want to do it all on physical testing, does not in any way mean that I would think that this was safe, that the evidence was there to allow me to actually say that this was okay, and I would not use that as the basis for being able to say that we could go, say that this was an adequate analysis from the point of view of taking that to court. So what did we look at in simulation specifically? So what we looked at was taking existing results from simulating based on accident databases and moving those to real time. And the observation we had was that as soon as we started looking at complex systems, and as soon as we started looking at areas in which cyber attacks were present, and from my point of view, a cyber attack, rather than thinking about it in terms of people with funny hats and glasses and people of that nature, you need to think about it as an attack outside of your model. An emergent property that you don't happen to like. So it is just the same as you're going to see from your emergent properties in these complex systems, but it happens to be done by somebody that is determined to do something bad to you. So when we tried to do this and tried to move those to real time, it was clear that actually, the use of historical data in order to work out what was going to happen was not something that we could actually get. The simulations were not correlated with the outcomes that we would have expected. We tried using things like STPA-SEC. We tried using all sorts of mechanisms in order to get better results out of the simulators, and were unable to get anything like a reasonable correlation. And that was true for digital systems, but it was particularly true when we look at the machine learning one. Second thing we looked at was things that were looking at gaming and model-based systems. So those simulators that come out of gaming and those things that came out of model-based. And we actually engaged with the Centre for Modelling and Simulation down in Bristol on the basis that they had both supercomputers and access to huge amounts of computing resource via cloud-based ones in relation to that. And we observed that actually that was actually bringing the capability in different ways. So the cloud-based one was in fact more capable than the supercomputer, but did not deliver it in a deterministic way. And that was the problem, because as it says on the third bullet there, we tried to, we were finding a problem how we replicate and prove that something is fixed. So we were able to demonstrate in quite a number of occasions that there was a problem. The trouble is when we ran the simulation again, because of, for instance, and in fact it's one of the papers that came out of Bristol on this one, because if we were running, I think, above about 4% utilization, we got to a situation on the simulator, even though it was supposed to be delivering the same results, so it was basically running a fixed thing, because of differences in the way the processors in a multi-processor architecture delivered themselves, because of differences in small timings and things, we actually got completely different results. So it was almost impossible to demonstrate, having demonstrated a problem, that it was fixed. So in a normal V&V and the sorts of things you'd be trying to do in terms of machine learning, it's, well, what conclusions can I actually get out of this? I can conclude that there is obviously a latent problem there, but I have no idea whether we fixed it or not, and whether we've got something coming out of it. The granularity and the fidelity of the model was proving to be a huge problem in relation to that. Every time we got to a particular point, so we looked at simulating functionality and overall functionality of a vehicle, which was great, but we moved simply to changing and doing things that then looked at timings on buses. So we moved to trying to do the timings on the buses as well as part of that, which was great, except once we did that, we started looking at timing inside the processors that were going with those sorts of things. And gradually this thing expanded to a stage where it was not possible to foresee. So just by doing something at a level gave us almost no information at all about the probability that there would be a failure in relation to that. And the last thing we had a real problem with was skills and access to resources. Yeah, the ability to actually push those things together and actually understand how people were operating in relation to that. Most of the simulators and most of the simulator skills that we were talking to people about, those that were done in academia, were not, for instance, looking at some of these wide scale areas. And we could not access resources that actually understood what were the failure modes of the simulator with respect to the type of domain that you were looking at. So we came to some conclusions. So we were looking at automatic selection of test cases. It was a requirement and we could not find a way to do that. But gradually we've managed to do that based on using AI systems themselves. We can't get probabilities about that in a way that would normally be satisfactory. But one of the things that we were looking at there is if we use the AI systems in order to drive the selection of automatic test cases, and we have a situation in which we have a relatively low standard of what we need going out, which we achieve by having a diversity in the outcomes and the diversity requirement, then we were able to actually get to a situation where we could automatically select test cases and operate rapidly in relation to that. Otherwise, there was no evidence that we were choosing the right ones. The gaming and model-based element there, we concluded that we actually needed a combination of these two things to be able to get the outcomes that we want. And elements like the deterministic outcome from the game theoretic, our observation was, and the conclusion from that is not an objective of the games industry. The games industry likes the fact it doesn't always do the same thing. So why we were expecting we would get something that was the same out of that, there was no real conclusion on that one. The combinatorial explosion, we started to put some rules in place about where you would need to use supercomputers versus where you could do cloud in relation to those. And it wasn't based on the types of things that you were simulating. It was based on the types of conclusions that you wanted to draw it. And we finally, I mean, part of our general observation in relation to that is that anytime you hit the physics, we got this combinatorial explosion. And one of the things that we put into our rules was an ability to pause at that point and find the right thing in order to do it. But that really compromised some of the timing critical elements of what we tried to do. We tried to find a way that we could achieve a conclusion in most cases without needing to go to these expensive resources, because if you need to do so, then it becomes unaffordable very quickly. And we failed to do so. So our conclusion was, all that happens is you slant what you're actually looking for, or you know, an attacker would slant what you were looking for, so that it was actually not something that we could count on a definite point at which you would need to go to those things. The defining the interface for service, we did define an interface for service so that we could plug other components into that one. And the cost of maintaining required specialist technology services. So it was really specialist stuff that we could not get access to most of the time, and it astronomically increased the cost of doing these activities. We looked at skills in medical robotics as one of the areas that we thought we would be able to find those. We were relatively disappointed there. We did observe that the UK actually has a lot of skills in adversarial simulation that come out of its military heritage, and we almost never use these on these areas. So the ability to apply intelligence back into simulation in real time doesn't form part of the simulation engines that we've been looking at, and doesn't form part of the simulation arguments that we've been hearing people talk about in relation to the machine learning and AI systems that they've been looking at. We concluded that simulation frameworks, things like Unreal, are not yet sufficiently flexible or granular to give us the outcomes that we required. We could not find the kind of granularity or the flexibility that we needed in order to adapt these in the way that you would need to adapt them in order to get a viable conclusion that you could take to court. And the access to capital, so the requirement for specialist compute might be difficult to capitalise. It's very difficult to stand up these kinds of facilities if you actually need to do that, which means they tend to be extremely uncommon and owned by certain industries that have a requirement to do them. And I will come back to that one. This was based on an analysis that we then did of the kind of techniques that you do when you're doing security analysis on these things, because obviously I do security analysis, just to an observation that these are all pretty static or pretty opinion based when we went in relation to that kind of stuff. And essentially they would not normally scale. We could not get them to scale. So the putting in the basis for why we wanted things, we had no confidence that we would be able to do this on large scale global systems and get an outcome. And this was going to be, this model, this requirement for what it as you want, was essential to being able to simulate effectively the outcomes that you wanted. But why does it matter? This is an extract from a thing here on braking systems. All of you, I'm sure, will have seen the Jeep element there, which essentially was an observation that we can take, which was Miller and Vasek's attack against the Jeep some years ago, which was based on work that was done prior to that in Hackams and things. The most important thing that came out of this was that as we were discussing things with people, nobody disputed the idea that it needed to be a safety critical system that was operating on your brakes. And what we did, firstly by doing survey and test, and then by looking at doing attack under controlled conditions, was to demonstrate first there were significant amounts of AI and machine learning and sensors in your braking system such that people did not actually understand that it was there at all. So the most common answer we got is there is no AI in our braking system. But if you look at what a modern braking system is, an ABS, so the ABS is actually looking to control braking, acceleration, steering, which is pretty much everything I need for my vehicle. It's got lots of sensors. When you're looking at high-speed emergency braking, that's looking ahead and making decisions about what people may be doing. So you've already got more than one set of type of machine learning and AI that contributes to this ridiculously complex system against which we want to provide safety critical data. And there isn't the normal thing that you would have expected on that, a failure mode by which you turn it off, because if you turn off an ABS system when you need it, that means you cause the crash, not that you prevent the crash. So all of those sorts of things actually turned out to be part of these sorts of systems. And we then set out 6 types of cyber attacks that you could not get rid of. So that we got contradictions in data streams, denials of service. And the point about those, they were equally applicable to the machine learning and AI systems or AI components of the system we were looking at. And they were, which meant that what you were fundamentally looking at was, what is the probabilities of failure, not will there be a failure? And it was not something that we could get our simulators to come out with a reasonable answer in relation to that was sustainable in any appropriate way. There was nothing there that we felt we could take to court in relation to that. So it was not actually giving us the answers that we needed. So to put it another way, if I have to actually control the harm, how is my simulator giving me an answer that allows me to do that? And just an observation there, the space for cyber attacks is infinite and always available was one of the conclusions that we have there. Just to be clear on that, I have loads of drunken conversations with my fellow academics about whether that's actually infinite or in practice infinite, but I don't really think that matters when you're looking at these things. And that's one of the really important things when you've moved from testing things in the way that you would have normally tested code to testing under simulation. You may move from testing 5% of the code to testing 15%, but it makes no difference in an infinite space, and it is not really very easy, and we have not determined that it is viable to actually it's a visualization technique to believe that you understand where issues will arise in your infinite space, and that I think is the thing that comes out of Rice's theorem and things that we need to make sure that we apply to what we think we're going to be doing in relation to that. So just coming back to this thing here, one of the things that we have there, and it's actually above the yellow diagram over on the left hand side of my screen, hopefully of your screen, the thing where it says vehicle dynamic simulation. This was a really important thing from our point of view. The observation there is in the automotive industry, there is a thing called the vehicle dynamic simulator. There are two of them that we're aware of in the industry. They were developed by McLaren and Williams as part of their Formula One activities. And the outcome of those is a massively capable simulator tied to various components, which allows people to reduce time to market by 3 years and the cost of vehicles by a similar amount in that aspect. But the point about that is a simulator from which you could viably get conclusions, not conclusions that are absolute, but you can get conclusions in relation to that. That starts to address some of the economics of how would you be able to maintain something of adequate quality to be able to do those sorts of things, and it starts to allow us to apply automatic candidate cases through a simulator to an automatic feedback loop that you would need on this kind of system, and to get conclusions in relation to that. It does so though only because we do other things. So coming back to what we said in relation to this, the most important things that we looked at were 3 principles. So we had to have things that increase the probability of detection, understanding and action. So we believe that simulation does nothing for improving the probability of detection. The model that you have may help with that, but it does not really normally improve the probability of detection. Understanding, however, it does improve your ability and your situational awareness if you construct it correctly in relation to the machine learning. Yet it does not give you an absolute, but it is an area where it can appropriately be used. Our conclusion when we were going through these things, we were unlikely when we looked at an automotive thing to be able to get better than a 50% probability over an 8-year period of time that we would avoid a catastrophic failure of an entire type of automotive, which is a really serious problem that you have in relation to that. And we suggested that if you're going to do that, you need to make sure that you increase the number of engineered differences. And why is that important? Because the inclusion of AI and the inclusion of machine learning is tending to remove some of the differences that are in these systems. So it has been underestimated completely how important the human being is in making sure that we do not get crashes simultaneously in all vehicles at the same time in the same way. And as we replace that with engineered things that are based on machine learning, we are in fact worsening our situation, increasing the probability of catastrophic failure, and therefore we actually need to explicitly counter that. And the simulation will help us with this, because it means that we can automate some parts of doing that, providing what we can actually do is go for a lower standard, find a way to go for a lower standard of evidence. And the other element there is the number of proactive updates. Effectively, what that's talking about is elements that have been designed against different models. So how many models must you have that will allow you to have a reasonable chance? Our belief is, and there may be other ways to do these things, that if you play these three things together, the mathematics that we can get from these in conjunction with the simulation would allow us to get a situation in which we could reasonably be taking the benefits that we get from the AI and the machine learning, which is certainly what we would hope for in relation to that. And we spend a lot of time doing mathematics that sat behind that and working out how all of those things fitted together so that we could integrate that into a function, so that you could basically go to court and say this is what my numbers looked like, as opposed to going there and waving your hands and saying I thought it was okay and obviously it wasn't. And we did those by actually putting some arguments that then we thought you would need to be putting behind those sorts of things. We felt that in the absence of this and simply saying I've got a simulator, it kind of doesn't answer the question. It neither has a statement there that's inherent about the granularity, and because we think the granularity, you think you need it. So if you look at engineered differences, we currently use things like Jaccard coefficients to look at the similarity between things, because one of the types of attacks that we'd observed was essentially logic attacks that cause you to have the system shut itself down. So essentially, it's like giving it a virus. But the point that went with those sorts of things is engineered differences. So not just differences, but the differences that you have there must be significant. And if what you find is in the light of changing circumstances, so in the light of changes in the environment that you're operating in, that is no longer the case. Areas that you thought you had significant differences may no longer be significant, and that need for a continual reanalysis. So we set out to make sure that it was economically feasible to do that, and you understood what you needed to do. And in the absence of that continuum, we do not believe that you can get a sensible outcome from the simulation for all the reasons that I talked about. So what should you take away? Stop pretending. We don't have engineering or scientific practices that guarantee to any legally satisfactory level the behavior of large-scale cyber-physical systems. And unforeseen circumstances are not unforeseen in the sense that we actually expect these things to take place. This idea that actually we've been dependent on human diversity for resilience in some of these systems, and that as we replace that with machine learning and AI systems, that will not be the case, means that we actually need to look at how will we change things around that. And the cyber techniques that can't scale increase liabilities. So essentially, looking at things that will only operate at small scale in relation to that, and knowing that you cannot increase it to the level that you would need to do that, is knowingly developing things that are deficient. And we feel that to a large scale, some of the simulation arguments are actually fitting into that, if they don't acknowledge how you put these things together. And that was kind of my quick talk, he says, and I appreciate you listening to me, and nobody interrupted, which was very kind of you. But I've got to the thank you bit.
Okay, so thank you very much, Peter. Can
I get rid of the presentation so that I can see people?
Yeah, you'll be able to see me, I think, at least.
I can see you.
Yeah. So do we have any questions from the audience? I mean, I have a couple. But I like to give people first dibs who are around in the audience. Yeah. So, but I'm not getting any so far, unless that's you putting your hand up, Ruth. Okay. So Peter, I had a couple of kind of more or less detailed things. Oh, well, one's so kind of general to begin with. The first one on this. What, given your conclusions, what do you think regulators should be doing in terms of what they're asking for and what the targets should be for these kind of things?
So if I went back to that slide, you'll note we had regulators on that one.
Yeah.
We were using examples coming out of regulation. So we were looking at UN regulations 155 and 156 at the moment, which were regulations about cyber stuff, which interestingly had come out of safety in the automotive sector. 156 is to do with software updates and is not restricted to the automotive sector. And our observation was everybody's just pushing things down the road. So what we were looking to do, so regulators were saying we need to do small scale things, we need to talk about things, small steps that we can take. And our observation was you're too late for that. You know, all of these systems are already in there, and the regulations are now, if they don't form an adequate basis for an industry to operate, then two things will happen. Firstly, the courts will reach for a piece of legislation like health and safety that will cripple what we're doing. And secondly, you'll find you're in the sort of situation that they're in Grenfell, where the regulators were not adequately regulating because the regulations were not adequate for the purpose, and you'll be just as culpable as everybody else is. So our argument in relation to that is we understand your problem, and the reason we based everything around a distributed ledger here was we needed to actually produce evidence of everything that we were doing on an ongoing basis, and they need to trust that as an ongoing continuum. I don't care if it's that or something else, but you need something of that nature that allows you to operate correctly. And just to give me give an example there, so in automotive, you can update providing you don't violate the type approval. Yeah, but there's no indication of what violating the type approval is. So and we were looking at and the stats that we were getting from extrapolating out from the back figures, where you were looking in the order of 250,000 updates per 8-year period that you were going to have to do. So if I had to do those by going back to the regulators, that would be wrong. So the regulators need to put in place regulations that allow people to operate in such a way that they can meet their objectives for evidence.
But to a certain extent, this kind of thing is happening already, because you have this whole dispute between Tesla and the US authorities on whether a software update that they put in place should actually have been formally a recall, and they should have put in a formal recall notification.
That's true. But I think.
And then what you're presumably seeing there is something where that structure is forcing Tesla to go much slower than perhaps it would want to. Yeah, in terms.
Yeah, absolutely. And your outcome from that would be the kind of thing you saw on the 737 Max, where it takes 18 months to get out a fix. Mm-hmm. But what you're looking at is societally important systems here that cannot be withdrawn for 18 months whilst we all figure out what to do about it. And you're looking at a pace. You're looking at.
Well, of course, for Boeing, then that was quite an important withdrawal. But anyway, yeah.
Absolutely. But the point is, it was quite important. But again, I think some of the conclusions you need to look at there are that is a symptom of a way of operating with respect to the regulators that is exceeding its ability to operate at the level of complexity they have already deployed, and that is orders of magnitude less than you're seeing in the medical sector, than you're seeing in the automotive sector, than you're seeing. It is orders of magnitude less than you're seeing in almost every significant deployment. So could you do the same thing that we have relied on to get such a good aircraft industry in all of these complex systems? My argument would be no. You can't do regulation that way. You have to do it. You have to do it a different way. So I'm agreeing with you on the Tesla thing. I just think there's a new dialogue, because if Tesla basically came back and said, "That's fine, guys, but I've got 250,000 updates to do over the next year, so over the next 8 years, so can you tell me that you've got enough regulators there to give me the sign-off then?" Yeah, the answer to that is almost patently going to be no, isn't it?
Certainly, yes. I mean, okay, so Craig,
we did just to put that into context, we did gather up statistics in relation to STPA and STPA-SEC as a way of doing functional things. We believed it would constitute 5% of the value of the vehicle to try and do an analysis in that way and have it reasonable, and it would not in any way guarantee that was actually solving the problem. But so at a fixed cost, but not a quantifiable outcome.
Okay, Craig Innes, you've got a question. Would you like to switch on your microphone and ask it? Maybe he's gone. I don't know. Let me look. Is he around? Yeah, he still seems to be here. Craig, are you there?
Stuart, his mic is broken. He's put the question in chat.
Yeah, I know. I saw it in chat. Yeah, Peter, would you like to have a look in the chat, or do you want me to read it to you?
I'll see if I can get out of the chat, eh?
Oh yeah. Okay, so he says it's broken. Okay, I can read it to you. You mentioned in your skills assessment part that the UK is not really leveraging its historic military knowledge of adversarial attacks. You mentioned, for example, that one could be funneling adversarial attacks back into the simulator safety assessment itself. Could you elaborate a little on what that process might look like?
So the observation there was that if you do fighter jets, then usually your adversary declines to actually send their fighters up so that you can work out whether yours is better than theirs. You accumulate, you do your best to simulate, but you accumulate information. You generally accumulate information every time you come across them in the air or every time you see them somewhere, and it is immediately fed back into the sort of things that you do in simulation. So it's a much more active learning situation from adversarial things. It's expensive, which is why I think things like the things that are actually there for benefit, so such as the vehicle dynamic simulator, are important to that. To try and do that just because I want to approve it, only a few people could even look at those, and it's still not effective, or it's still not necessarily effective in relation to that. But I think if you're not feeding that kind of intelligence information immediately back into your simulators the whole time, then you're always working on static models that are generally out of date, and generally, leaving aside my active attacking of it, yeah, it will. There's a really high risk that will not be doing what you think it is.
Okay, so good, thanks. I had we've still got a little tiny bit of time left. I had two questions, and maybe you could. One of them might be long, and the other might be short. One of them is relevant to this. If you look at the way that Waymo construct their simulators, then they use real-life driving data and feed that into the simulators, and then use that to produce variants on it. Is that along the lines of what you're suggesting in terms of from military experience, feeding back from every encounter into the simulation?
It is, I mean, and that's a good start to the sort of thing that you should be doing in relation to that. But it kind of comes without, in Waymo, it comes without the intelligence that's attached to that. It's not what does that mean, and I think the simulator part of what does that mean, yeah, is a really important thing that we need to feed into these things. You know, it's the sort of thing that we always find when we get large-scale AI systems. They're equally capable of being deluded that I am.
Okay, that's good. Thanks. And then this is potentially could go on forever. So I hope that you probably shut me down quickly on it. When you gave the ABS example, you had 6 potential security kind of.
We had 6 types of cyber attacks that you can't.
Yeah, 6 types of attack. Then were they predominantly? I mean, where did they happen? Was this on the road or was it in production? Because it seemed like some of them seemed to be at the stage of when the systems were being, if you like, developed or manufactured or tested rather than deployed. You know, so what phase in development did you see those coming in?
They're always there in operation.
You think it's always in operation? So
I mean, when you do a design, you often don't recognize it. So that was one of our observations. Nobody could have written the probability statistics that they wrote for a braking system, you know, and to have acknowledged the 6 types of problems they had.
So to avoid a complete shutdown of a type, yeah, you'd be recommending that nobody could get anywhere near a car in remotely. Yeah, that's the.
No, not at all. What I'd be saying is you need to acknowledge that. So much as I don't like the fact that it may be my car that crashes, you know, we can ensure the fact that 1,000 cars crash every year. Yeah, if you could say that's what you're going to get as an outcome, 1,000 are going to crash, that wouldn't be a problem. Your problem is you can't say that, yeah, and you're saying every car may, or you're saying, yeah, it's as I say, when we basically got 60% of this type would actually have this problem on the road, that's a very large number. It's an uninsurable number. Yeah, and that is the difference between an electromechanical system where I can saw through the brakes and have somebody crash. Yeah, and a digital system where essentially it's got a common mode failure based around attacking parts of your digital system.
Yeah, I suppose that I was interested in the whole issue about data and learning, because most machine learning systems that are actually deployed these days are locked. I mean, at least in safety systems where
it is locked. But the problem about that, it's locked, but you can change the environment. So you're right, the system is locked, but effectively you change the environment that feeds into it, because they're not standalone. They're part of a complex system in their own right.
Hmm. Okay, so I must have misread. So I'll go back and look at this slide. I must have misread some of the potential attacks. Yeah, because
so the attack was based on. So what you get is error correction going into. It's the error correction that you attack in order to poison the machine learning that's operating on the sensors, so they don't actually produce the right answer. So it's because it's all coming off similar silicon. You know, nowadays what you do is error correction on silicon in order to get the stuff back to being something that's approximately digital. And for a sensor, you use as much capability as you can, obviously. So to get the machine learning operating over a domain that it expects to operate over, you basically normalize the results slightly using an error correction, and then you run the machine learning on that. But actually, you can change that error correction because in the chip, and you can, yeah, and on a LiDAR, for instance, you can do that by flashing lights at it.
Okay. So I think, well, you've answered all my questions, and if the rest of the audience is a bit quiet, then it would. I mean, it'd be good for at some point. I'm going to come back and ask you about what you think regulators should be doing, since that's since I think that's still an interesting issue. Yeah, that we could probably come back on. But anyway, thank you very much, and I think another round of applause is probably well deserved. And thanks very much.
And I hope that was at least of interest to somebody.
I think it was definitely of interest to everybody. Yeah, thank you. Thanks for a talk. Yeah.
Thanks very much, and appreciate the time.
Okay, good. Thanks. Bye now. See you again, Peter.
Cheers then. Bye.